So now we're going to get into the section of the course that deals with meteorology and weather forecasting, things like that. And before we start that, we have to look at the atmosphere because the atmosphere is where we live. We walk around in the atmosphere. We walk around on top of the lithosphere, which is the ground, but we walk around and breathe in the atmosphere. So the layers of the atmosphere, you've got the troposphere, which is really where we live. That goes until about a mile up or so. Until that's the airplanes usually fly around the top of the troposphere. The troposphere is the bottom layer. This is where the important weather patterns happen because they're important to us. What happens above that doesn't really matter to us very much. Temperature decreases with altitude as one goes higher. Just like in mountains, the temperature tends to go lower. If you're in an area with mountains, like Las Vegas, for example, it's warm, but then as you climb the mountains that are close to the city, it gets colder and colder. Okay, the temperature tends to decrease with altitude, called the environmental lapse rate, and the average is about 6.5 degrees Celsius per kilometer. Kilometer is 1,000 meters, which is the same as about 3.5 per 1,000 feet. In other words, a kilometer is 1,000 meters, which is actually about a little over 3,000 feet. But anyway, the point is that if it's 20 degrees Celsius, which is about room temperature on the ground, so if you go up 1 kilometer high into a mountain, in other words, it'll on average be about 13.5 degrees. It'll cool off, in other words. The thickness varies in terms of the thickness of the atmosphere itself, of the air. Average height is about 12 kilometers. If you go above that, you're not going to have much oxygen. And generally, as you go up, you're going to have less and less oxygen. Moisture is contained within the troposphere. All the air moisture, and certainly there's plenty of moisture and humidity in the air that we breathe, is in the troposphere. So planes flying in the troposphere go through areas of moisture. If they're flying above the troposphere, there really isn't going to be any moisture up there. As one rises through the troposphere, air pressure, density, and temperature all decrease, and the boundary above the troposphere is called the tropopause. Then we have a slide on the troposphere and the mesosphere and the thermosphere. But before we do that, I need to show you this little diagram over here. I think this will help you understand a little bit about the troposphere in general. Now, about the atmosphere in general. You have these different layers. The lowest layer is the troposphere, which goes up until about 10 kilometers, about 6 miles up in the air. Mount Everest is almost as high as the tropopause. Airplanes fly somewhere around here, around the tropopause. Over the troposphere, you have the stratosphere, which is the next higher up. As you go further up, then you have the mesosphere, and then the thermosphere, which is way up here. And the in between each layer, you have the pauses. On top of the troposphere, you have the tropopause. On top of the stratosphere, you have the stratopause. On top of the mesosphere, you have the mesopause. This is the temperature, which is actually very interesting, that as you go further up to the tropopause, it gets colder and colder. If you've ever been inside an airplane where they have these, the external temperature gauges, on the ground, when you take off, it might be 60, 70 degrees Fahrenheit, which is about 20 degrees Celsius. As you go further and further up, it gets colder and colder. For example, on a nice summer day, you might look at the external temperature gauge in your airplane, and it says that the external temperature is, negative 40 degrees or something, even though it might be perfectly warm on the ground, because where you're flying is way up here around the tropopause, and the temperature is very cold. Interestingly enough, as you go further up into the stratosphere, the temperature actually increases until you get to the stratopause, and then in the mesosphere it decreases again. I don't know what that meteor is doing there, and the auroras. But then you get to the thermosphere, and the reason why it's called the thermosphere is because it's hot. That's therm means like thermometer temperature. It gets hotter in the thermosphere all the way up here until you get all the way to outer space, and then the temperature drops kind of to like absolute zero. Okay, so the troposphere is all the way on the bottom, and that's the one we're really concerned with because that's the one we actually live on. Then you have the stratosphere, which starts at about 12 kilometers up, goes to about 50 kilometers up, as you can see from this diagram. Temperature increases at the top of the stratosphere. As you go further, it goes up, and near the top of the stratosphere, here's the ozone layer, the famous ozone layer that keeps us somewhat safe from sun's rays. the one that was depleting because of human activities until a few decades ago, but we won't worry about that right now. Uh, Air pressure is about 1 millibar at the top, which is very, very low. Just to give you an idea, around the Earth's surface, air pressure is about 1,000 millibars. One atmosphere is, I guess, a little bit, roughly 1,000 millibars. And so you can see how the pressure just decreases. As you go up, the pressure just gets less and less. Air pressure is relative. You don't see it on this chart over here, but it's much. The pressure gets much less. Temperature varies and goes back and forth, but pressure gets less and less, and moisture also gets less and less. Moisture starts in the troposphere, and then up here there is no moisture in these levels. Pressure also gets less and less as you're going up. And that's why the pressure is so incredibly low, only 1 millibar at the top of the stratosphere. Has some advantages for long-distance flights. That's why long-distance flights very often go up into the stratosphere. Long-distance flights go up past the tropopause and fly somewhere around here, at 37,000 feet, which is somewhere in the lower reaches of the troposphere, where it's quite cold, of course. But I guess there's not as much weather. There's not as much moisture to play havoc with the airplanes flying. Then you have the mesosphere. I'm sorry. Oops. Okay. The advantages of flying in the stratosphere is that it's above the storming weather, it has strong, steady winds, and it lacks the turbulence of the troposphere. That's why there's more turbulence in takeoff and landing usually than when you're in the air. Now, you could have turbulence even in the stratosphere. You could have winds going back and forth, knocking the plane around a little bit, but you're more likely to have turbulence in takeoff and landing. The outer boundary at the top of the stratosphere is called the stratopause. On top of that, you have the mesosphere, which starts at about 50 kilometers and ends at about 80 kilometers above sea level. The temperature decreases as you go up, starts over here, goes down, 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 down till it's extremely cold. And the outer boundary of that is the mesopause, and then finally you have the thermosphere, which is hot. It's the outer area of the atmosphere. There's no real well-defined upper limit. It just kind of fades away into outer space. The gases are moving at high speeds. It has a very small percentage of the mass in the atmosphere of the gases. There's an International Space Station in the thermosphere. In other words, this is so far out. If you were all the way out here in the thermosphere, it would look basically like space. It doesn't, you don't have like the blue sky like you do. If you look up from the thermosphere, it would be totally black, like you're in outer space. The space station in orbit around the Earth are actually in the thermosphere, so it's kind of hard to tell the exact difference between outer space and the thermosphere. And it has an extremely high temperature because the air is so thin. But because the air is so thin, it actually has the effect of being very cold. If you walked out there without a spacesuit in the thermosphere, you'd freeze. And the reason is because even though the temperature is hot, the molecules are moving fast. There are so few of them. There are so few actual molecules floating around that the heat can't be transferred to your body efficiently. So you'd freeze even though the temperature might be 300 or 400 degrees Fahrenheit. So anyway, kind of ironic. So that is the structure of the Earth and the Earth's atmosphere. Now we are moving to weather patterns. And this is obviously a much different topic than we just covered in terms of the atmosphere of the Earth, but this is really about weather patterns. There are 4 dates in the Earth that are significant in terms of weather patterns for the Earth, in terms of seasons, and those are the solstices and the equinoxes. Now, the reason why this is relevant is because the Earth is tilted towards the Sun at various angles at different points in the year. This is a diagram of the way the Earth looks relative to the Sun at various times of the year. See, there are 2 times when the Sun's rays, because the Earth moves around the Sun and the Earth is tilted on a 23.5 degree angle, but because of that, depending on where the Earth is relative to the Sun, that will make a determination of how the Sun's rays directly impact the Earth. At this time of year, for example, when the Earth is facing the Sun like this, the most direct sun rays are in the middle of the Earth. The middle of the Earth, of course, is called the equator. These measure latitude lines. The equator is 0 degrees latitude. It's smack in the middle. The poles are 90 degrees latitude. This is 90 degrees north latitude. That's the North Pole. This is 90 degrees south latitude. That is the South Pole. But at this time of year, the sun is shining directly on the equator. The Earth is kind of staring right, the sun is staring right at the middle of the Earth, and the same thing when it's down here. When the Earth's over here, as you can see, the sun is shining in this direction, and it's shining more towards the southern hemisphere because the Earth is kind of tilted away from the sun. Whereas over here on this side, the Earth is tilted towards the sun, and so the northern hemisphere is getting more direct sun rays. These areas where the sun is shining directly on the middle of the Earth, on the equator, are called the equinoxes, from the same word as the word equator or equal, when the sun is shining directly on the middle of the Earth. And the other two are called the solstices. The solstice on this side is the summer solstice for the south and the winter solstice for the north, because that's where the sun is shining directly on the south, and that is in late December, our time. That starts winter in our time. And on the other end, you have the summer solstice in the north, or the winter solstice in the south, where the sun is shining directly on the northern hemisphere, and that is in late June, our time. Now, of course, that's not really the hottest and coldest time of the year. As we know, the hottest time of the year in the northern hemisphere is actually usually in late July. And the reason is because even though the sun is shining most directly on the Earth in June, it takes a while for the land to get heated up. It takes a while for the land and the water to get warmed up. So there's about a lapse of a month from the time that you have the summer solstice till the times that you have the hottest time of the year. And the same thing is true with the opposite. In December 21st, 22nd is the winter solstice in the north. It takes about another month until late January for it to really be the coldest time of the year. But those are the 4 dates that are critical. You have the autumnal equinox, namely, let's start with the solstices. The solstices are in June and December. The location of the sun's vertical rays are, remember, because of the tilt of the Earth is 23.5 degrees, on the summer solstice in the north it is 23.5 degrees north, which is also sometimes known as the Tropic of Cancer, and in December, namely the summer solstice for the south and the winter solstice for the north, the Earth is tilted away from the sun, and therefore the direct angle is 23.5 degrees south latitude, which is the Tropic of Capricorn. Let's put that diagram again up to explain it. Where did that diagram go? There it is. So again, this is December, because you see these 3 lines over here? The middle one is the equator. The southern one is 23.5 degrees latitude south. So it's closer to the equator than to the pole, but still somewhere in the middle over there. That's the Tropic of Capricorn. In the north, you have the Tropic of Cancer, which is 23.5 degrees north. Give you an idea of where that is in terms of the United States, that's around just beneath the southern tip of Florida. So the southern tip of Florida on June 21st has the sun practically right above its head. You know, Florida's right around over here on the Tropic of Cancer. New York is about 41 degrees north latitude, so it's about 18 degrees further north. So New York actually never has the sun right above its head, because the furthest the sun directly shines on in terms of north is 23.5 degrees. So these are the solstices. The summer solstice in the north, the summer solstice in the south, the winter solstice in the north is this one, December, and the winter solstice in the south is this one, in June. So those are the equinoxes. Those are the solstices. The equinoxes are the opposite, where the sun is shining directly on the equator. The Earth's axis is not tilted towards the sun or away from the sun. Now, this also affects the amount of daylight you have and the amount of nighttime you have. On the equinoxes, the whole Earth has 12 hours day and 12 hours night. You can see because the Earth spins along this direction, along the direction of the latitudes, along the direction of the equator and the tropics. So the Earth spins like, it's hard for me to show it on a 2-dimensional diagram. Although thankfully the internet has some examples. Here's an example of the rotation of the Earth. You can see how the Earth is rotating here, where this would be an example where it's summer in the northern hemisphere. You can see how the Earth is kind of tilted so that, this would be a line on the equator. Notice how as it's moving along, like look at these same clouds in the diagram, they're kind of going down a little bit. But the Earth is tilted. Notice how it's tilted more to the equator, where areas in the northern hemisphere are going to be more in the sunlight more than areas in the south. Let's say if we take an area in the north, see how much time it spends in the sunlight. Whereas in the south, if we take, Australia over here, we'll wait till Australia comes around again. Where's Australia? This is Africa, and then this is South America, and let's look at some place southern, like the bottom tip of Australia over here as it should come into the picture any moment now. Where is it? There it is. See, Australia doesn't spend that much time in the sun. It kind of comes in and comes out right away, whereas something like, something in the northern hemisphere, like Europe, spends a lot more time because of just the way the Earth is tilted towards the sun this time of year. In the winter, in December, January, that would of course be the opposite. So if you look over here, this is an example of actually our winter, where the Earth is tilted towards, this would be like in December, where the Earth is tilted towards the southern hemisphere. You can see as the Earth rotates, something down here is going to spend a lot of time in the sun and very little time at night, whereas something all the way up here, like New York, somewhere in the northern hemisphere over here, is going to spend a lot of time at night as it rotates and is going to spend very little time during the day. That's why days are much longer in the summer than they are in the winter. And also in the winter we get much lower direct rays. If we're over here, we're in the north, which is way up here, our angle of insolation, which means angle of incoming solar radiation, which means angle of incoming sunlight, is going to be at a much lower angle, much less direct than the people down here that are going to get much more direct sun rays, and therefore it's going to be hotter for them. That's why just over here, you can see a little diagram which indicates that the more direct the sun rays, the hotter it's going to be, generally speaking. Over here you have the tropics. You can see the palm trees in the left diagram over here. These have direct radiation. Let's say in the tropics they have direct insolation, direct sunlight, and so therefore they're hotter. In between, where you have regular forests and farms, places like the United States, mainland, you have the sunlight is kind of at an angle, which makes it warm but not hot. And then you have up here with the Eskimos and the igloos, and in the northern Canada or Alaska, Siberia, you have much lower radiation, much lower angle of sunlight, which tends to make it cooler. Okay, we saw this diagram already. This is just one example of all three kind of combined in one diagram. This would be where it's in June, the northern hemisphere summer, where you can see in the North Pole, because remember the Earth is spinning like this, which means the North Pole never even gets out of the sunlight at all. Just on this diagram, which I showed you before, look at the North Pole. The North Pole's around here, right up here. Now the North Pole doesn't spin at all, it just kind of sits there. The North Pole is never getting out of the sunlight. So like in this diagram, if you notice, the Earth spins like this, but the North Pole is going to be daylight for 24 hours, whereas the South Pole is going to be nighttime for 24 hours. And in the further you get from the equator, the further north you get, the more daylight you have. You see, the more percentage of the Earth is in the daylight, and the further south you get, the more nighttime. So, in December it's the opposite, of course. The further south you are, the more daylight. The further north you are, the more nighttime. On the equinox, September or March, everything is 12 and 12. Everything is 12 hours day, 12 hours night, because the sun's rays are directly in the middle, and half the Earth is day and half the Earth is night. Now, it's always going to be half the Earth is day and half the Earth is night, because whenever you shine a light on a ball, half of it gets lit up and the back half doesn't get lit up. But when you have a tilt, and you can try this with a ball at home, it's very easy to see. If you spin around a particular point, you'll see the further you are towards the edge of that point, the more extreme you're going to have in terms of the difference between daylight and nighttime hours. And that brings up the issue of how the atmosphere gets heated. Again, we're talking typically about the troposphere, because that's the one we're concerned about. That's the one with the weather patterns that affect us. Heat is thermal energy. That's really all heat means. Well, heat is actually the speed of the molecules, but for our purposes, that's the same thing as saying thermal energy. Again, thermal comes from thermometer, really means heat energy. It's kind of a tautology. Heat really is the same thing as thermal energy. They mean the same thing. And heat is transferred from warmer objects to cooler objects. When you put an ice cube in the cup of hot tea, well, the ice cube's going to melt very quickly because the heat of the tea is going to flow to the ice cube of the to the cold molecules of the ice cube, and eventually the whole thing is going to settle somewhere in between. It's going to cool the thing off a little bit, and the ice cube is going to melt. The temperature is the average speed of the molecules, average kinetic energy of all the materials, atoms, and molecules. How does heat get moved from one thing to another? Well, there are three basic ways. Number one is conduction. That's the moving of heat through solid material, like a blech on Shabbos. You turn on the fire, and one part of it is on the fire, the rest of it gets heated up dramatically. You heat up one part of a radiator, the rest of it gets heated up very quickly. Then you have convection, which is through the air. Like you put something in an oven, the hot air rises and kind of spreads out across the entire oven through hot air rising and then spreading out throughout the entire room. That's convection. Then you have radiation. Radiation is just the transfer of heat through open space. Like the way the sun heats up the earth is just through solar energy rays, through solar rays, light rays, which have energy and cause heat, go straight from the earth, from the sun to the earth and the other planets, and around space in general. Those are the three basic ways that heating happens. In determining what kind of a temperature you have in a particular area, you can figure out the average. This is all pretty simple stuff. If you want to find the average temperature for a given day, you just add up the two given temperatures and divide by 2. So if the maximum temperature is 57 Celsius, 57 Celsius is about 135 degrees Fahrenheit. So I'm just going to change that to Fahrenheit because that 135 degrees Celsius is seriously hot. So if the average is 57 Fahrenheit and the low temperature is 23 Fahrenheit, so you want to figure out the average, just add them together, which is 80, and divide by 2, so the average is, again, 40, not 30, but either way. If you want to find the range of possible temperatures, just simply look at the difference between the high and the low. If the low was 23 and the high was 57, so the range was 34. If you want to look at a real-life example, maybe we can look at the weather.com temperature ranges for today and the next 10 days. This happens to be for Muncie. We see today we have a high of 41 and a low of 30. You can see, wow, later in the week it's going to get seriously cold. So let's say the average temperature for tomorrow, well, assuming that the high is 33 and the low is 17, so you add them together, 17 plus 33 is 50, and the average is 25. So and tomorrow's range would be 33 minus 17, which is 16. So the high of 33 and a low of 17 means you have an average of 25, which is smack in the middle, and a range of 16 degrees from high to low. If we want to take Friday's high and low, the low is 2 degrees Fahrenheit, then the high is 17 degrees Fahrenheit. So that means the average is 2 plus 17, which is 19, divided by 2, which is 9.5, and the range is 15 degrees. On Thursday, high of 30, low of 12, so the average is 42 divided by 2, which is 21. And the range is 30 minus 12, which is 18 degrees from high to low. Again, fairly simple, but when they report those things in the weather, you should know what those mean. Okay, the annual temperature is the same basic idea. The annual temperature, they look at the high for the year and the low for the year, the average of the mean temperatures for every day for the entire year. The annual temperature range is the difference between the highest and the lowest. I mean, where I live in the New York area, the lowest is usually around 0. This Friday they're talking about a low of 2. That's probably about as low as it's going to get. Probably not going to get much lower than that. The high temperature is usually around 100, let's say 102, 103, something like that. Maybe in the summer, once in a blue moon, you get temperatures that high. And the difference between the average temperatures of the warmest and the coldest months, you can measure these things pretty much any way that you'd like. I mean, just to give you an idea. Let's see. So this is an example of the calendar for December, and then you can look up pretty much any of these things. Average monthly temperatures, average yearly temperatures. You just look at the average temperatures for the individual days, and you can determine the average, just like you would determine the average of anything else. What determines temperature? What controls temperature? Well, the most important thing is the receipt of insolation, or incoming solar radiation, or just plain solar radiation, or sunlight, whatever you want to call it. Receipt of sunlight is the thing that causes the temperature to increase. Lack of sunlight, or indirect sunlight, is the thing that causes the temperature to go down. Other important controls are a differential of heating land and water. Land has a much lower specific heat, a much lower heat capacity than water, which means that water can absorb heat much better, which means it's much harder to heat water than it is to heat land. So therefore, if you have an island that gets the same amount of sunlight as a place in the middle of the continent's going to have much more extreme temperatures. It's going to be much colder in the winter and much warmer in the summer than the island, because in the island you have the water around it which absorbs the heat and the cold, causing the land to have a much less temperature variation. So land gets hotter than water, land cools rapidly than water, which matters, of course. Let's look, for example, at a map of the United States to illustrate this. This is the United States. I'll make this a little bit, not that small. Well, anyway, let's look at the United States over here. All right. There we go. All right. Anyway, so in the United States, you have... I'm just going to leave it like this. I don't want to play around with it too much. Anyway, wind patterns, because of prevailing wind patterns, weather patterns tend to move from west to east. In other words, weather patterns tend to start around here and move in this direction. So weather patterns on the west coast tend to be quite moderate. In other words, doesn't get too hot, doesn't get too cold. And the reason for that is because it's moderated by the ocean. The weather patterns tend to come from the ocean, which don't get too hot or don't get too cold. So in Washington, for example, which is further north than New York, New York is down here, and certainly it's further north than Nebraska, Iowa, these areas, and yet Washington in the winter is much, much more mild than these areas in the middle of the country. And in the summer, it's also much more mild. In Seattle, for example, in the winter it might be in the 40s, and in the summer it might be in the 70s or 80s, whereas in the middle of the country it's going to be much hotter in the summer and much colder in the winter, even though they're actually closer to the equator. So a place like Iowa is famous for being freezing cold in Minnesota, famous for being freezing cold in the winter, and yet they happen to even be further south than Washington, which is much more moderate, because these continental climates it takes a very short time to heat up, very short time to cool down, so their weather patterns are much more extreme. On the East Coast in New York, in this area, on the one hand, the weather patterns tend to come from the middle of the country, which tend to be very hot or very cold, but on the other hand, as the air masses tend to approach the ocean, they are moderated a little bit by the fact that you have the Atlantic Ocean over here. So temperatures in New York are colder and hotter than they would be, for example, in Oregon and Washington, but on the other hand, not as cold and hot as they would be in Minnesota and Iowa and these places over here. The middle of the country tends to be extremely hot in the summer and extremely cold in the winter. New York a little bit more moderate, and the West Coast, of course, much more moderate than any of these places because their weather systems all come from the ocean. Things that matter also have to do with altitude. The higher you are on a mountain, generally speaking, the colder you're going to get. And of course, common sense, cloud cover. The cloudier it is outside, the more rainfall a particular area has, the less hot it is going to be. The more, if there's no clouds, like in a place like Phoenix in the deserts, it's going to get extremely hot because there's nothing to block it. Whereas if you have other places that are a little more humid, places that could even be further south, they're going to be a little bit cooler. Just to put the United States back over here. This is where Phoenix is, a desert, and this, for example, is where Houston is. Where Houston is further south than Phoenix, much more humid because it's near the Gulf of Mexico and for other reasons too. And so Houston, which gets hot, is still not going to be as hot as Phoenix because it's going to have more cloud cover, which is going to block out at least some of that heat. Some other things that tend to moderate temperature: geographic position, windward coast. If you have a mountain that is toward where the wind is blowing, in the United States it would usually be on the west part of the mountain because that's where the wind blows from west to east. In those areas you have cooler summers and milder winters because you have the ocean moderated air that's being blown into the mountain. Whereas the other side, the leeward coast, in other words, the coast on the other side of the mountain, is the mountain acts as a barrier and blocks the moderate air from being blown in. Just to give you one example, if you look at mountains, this is, of course, the southwestern part of the United States. Here's Los Angeles, San Diego somewhere, all the way down on the chart over here. Here it is, in case you didn't see it. This is Las Vegas over here. There's the Sierra Nevada mountain range, which are over here, and there are various other mountains around here. And that means that places on the windward side that are getting the air from the moderate ocean tend to be more moderate. Places like San Diego are famous for having beautiful weather. Los Angeles has relatively moderate weather. The summers don't get too hot, and the winters don't get too cold. And whereas on the other side of the mountains over here, places like Las Vegas get extremely hot in the summer. They get in the winter they don't get that cold, but they get relatively cold. Certainly much colder than places on the other side. Certainly much colder than places like Fresno and Bakersfield. And then you have like Phoenix, which is a little further over here, which is extremely hot in the summer, and in the winter it's still not that hot, but relatively cool. Sorry, not that cold, but relatively mild. Also, the southern hemisphere tends to have milder winters than the northern hemisphere. And when you see a globe, a map of the entire Earth, I think it'll be pretty apparent as to why. Now, this is not big enough, unfortunately, to get the entire globe into one. Well, let me find a globe. Anyway, here is basically a map of the entire Earth. And one thing you may notice is that the northern hemisphere has a lot more land than the southern hemisphere. The equator is this line over here. The equator starts over here and goes all the way, it goes all the way across here. So this is about the equator. So north of the equator, you have most of Africa, almost all of Asia, all of North America, even part of South America, and all this landmass. In the southern hemisphere, the only thing you have is the southern part of Africa, which is very narrow, South America and Australia, and most of it is ocean. So the southern hemisphere tends to have more mild winters and more mild summers than the northern hemisphere, simply because there's a lot more water in the southern hemisphere than in the northern hemisphere. And so, in places like Russia, for example, the coldest parts of the Earth, in case you're curious, are around here, like in Siberia. I think Yakutsk is over here, like they have on the risk board, somewhere around here. But it's extremely cold, A, because it's far from the equator, you can see that, but also because there's so much land that doesn't moderate the temperature. A place that's really far north, like Norway or something, or England even over here, but if there's a lot of water around it to moderate the temperatures, it tends to not be as cold. Whereas in northern Russia over here in Siberia, you have a huge amount of land that gets cold very quickly, and that's why these areas are the coldest places on Earth, except for Antarctica, which is all the way at the pole. So that's why, in general, the weather is a little bit more mild in the southern hemisphere than it is in the northern hemisphere. The next chapter, chapter 17, is about moisture, clouds, and precipitation. We're going to be discussing air masses, precipitation, general things about climate and moisture. And moisture also has a lot to do with air pressure because, as we'll discuss a little bit later on, pressure tends to have an inversely relationship with moisture. When you have a lot of pressure, the moisture tends to get blown away because it gets blown to areas with low pressure. And when you have low pressure, the moisture tends to build up because the water particles that are in the air tend to get blown in from areas with high pressure. So air pressure, which is also known as atmospheric pressure or barometric pressure, is pressure exerted by the weight of the air above. We don't feel it because the air pressure is pretty constant all around us. The air pressure below our bodies and right and left of our bodies are pretty much the same, so we don't really feel the pressure, but there is plenty of air pressure that's all around us at all times. The best indicator of current or changing weather conditions is pressure. High pressure acts as a barrier to approaching weather systems. If we're sitting in an area with very high pressure, well then storms that are coming towards us are going to be blown away. Wind goes from areas of high pressure to areas of low pressure because high pressure blows. There's a lot of air movement, and so it moves towards areas of low pressure. So if you're sitting in an area with high pressure, it's not going to usually rain, it's not going to usually be very cloudy because the clouds and the water particles are going to blow away to areas of low pressure. On the other hand, areas of low atmospheric pressure is the path of least resistance for a weather system, since that's the way it's going to be blown anyway. So it makes it more likely that if you're going to have low pressure, you're going to be associated with increase in storm activities, and therefore high pressure area indicates nice weather, whereas low pressure indicates that storms are more likely. When people are in ships on the water, if they see that barometric pressure is high, they can usually relax, maybe go to sleep, whatever it is. If the area of barometric pressure is low, they have to worry that maybe storms and rain are going to come, and they might have to deal with that as well. The reason for that is areas of high pressure blow everything away, whereas the pressure and moisture from the area of high pressure blow into low pressure areas, indicating precipitation coming from the warmer air mass. Okay, how do you measure air pressure? Well, the answer is you measure it in millibars or inches. That there's no real inherent difference between them. But millibars is one type of scale. Inches is another type of scale, but they're both based on barometers. Barometers is the instrument that is used to measure air pressure. Air pressure at sea level, 1 atmosphere, I mentioned before, was about 1,000 millibars. It's actually 1,013.2 millibars. In inches, it would be 29.92. It doesn't really matter. There's no real inherent difference between them. They are just different scales. Pressure could be based on mercury, just like a thermometer is sometimes used with mercury because that measures the temperature. It expands as the temperature goes up. Well, the same thing is true with pressure. When the air pressure increases, the mercury in the tube rises and is used for weather predictions. If you're sitting there and you see the pressure going up, you could probably tell people that it's probably going to be a nice afternoon. If you see the pressure's going down, you say it's very possible that rain is coming in. You could also have an aneroid barometer, which is the same, measuring air pressure without any liquid. Mercury is a liquid, but an aneroid barometer works without any liquid. It has a partially evacuated metal chamber, which turns a dial for the changes in air pressure. Again, that's not really critical, but the only thing that really is critical is that aneroid barometers do not use liquid. They measure things in using as millibars, and it can be connected to a barograph, which continuously records pressure change with the passage of time. Pressure change might actually be more important than the pressure itself, because if you see pressure is going up, that probably means that the storm, if there's a storm, it's abating and it's going away. Whereas if the pressure is going down and there's a storm, it's probably going to intensify. I was just reading a book about a ship that was in a typhoon in World War II, and when the pressure was going down, it means the typhoon was going to intensify. Whereas when the pressure started going back up, they realized that they might be out of the woods, so to speak. The next factor is, of course, humidity itself. Humidity is based on the percentage of water vapor that's in the air as a percentage of how much the air can hold. The air can only hold a certain amount of water vapor. If there's more than that, it's just going to rain and it's just going to empty out. And that is measured in percentages. 0% would be no humidity at all. 100% relative humidity would be saturation. That's the maximum quantity of water vapor that the air can hold. If there's 100% saturation, it's probably going to rain at some point, although there's no guarantee. There could be 100% relative humidity with no rain, and there could also be rain without 100% relative humidity. But the higher the relative humidity, obviously, the more of a chance for rain you're going to have. So relative humidity is the ratio of the actual water vapor in the air compared to the amount of water vapor necessary based on that temperature and pressure. Generally speaking, the higher the pressure, the more water vapor the air can hold without raining, and the higher the temperature, also, the more water vapor the air can hold. The hotter it gets, the lower the relative humidity, because as it gets hotter, the air can now hold more moisture, and so therefore, if you have the same amount of moisture and it's 60 degrees, and then you have the same amount of moisture as 80 degrees, the relative humidity is going to be much lower in the 80-degree weather, because the air can hold more vapor, and so the percentage of how much it actually is holding is less than the total relative to the total of what it can hold. So the lowest humidity is usually around mid-afternoon because that's when the temperature is the highest, whereas the highest humidity of the day is usually in the morning when you first wake up around sunrise because the temperature is lower. The dew point is the temperature at which you have 100% relative humidity. The dew point, if you have 100% relative humidity at a particular temperature, that is the dew point. For example, now let's say winter, it's a bad example. Let's say a summer day, it's 85 degrees, and let's say the dew point is 65. That means if the temperature would go down to 65, there would be 100% relative humidity. If the highest dew points we usually see as a practical matter, the highest dew points are usually probably in the mid to high 70s, I would say, at least in the New York area. So if it's 75 degrees and 75 degrees is the dew point, it means we have 100% relative humidity. That's when measures actual moisture content, and that's where water vapor condenses into a liquid. So at 100% relative humidity, you're much more likely to have rain. Now, calculating relative humidity, you can see there's a whole slide over here. I'm not going to get really into it because there's no real way you can calculate relative humidity unless you have a chart. A chart would look something like this, where you would measure the dew point, the dry bulb temperature and the wet bulb temperature. Dry bulb temperature means the temperature it is outside. Wet bulb temperature, it means the temperature of something that is condensed. Not necessarily the dew point, but the temperature if you would dip something in water and then put it outside, what would its temperature be? It would be a little cooler because water tends to cool everything down, so that would be the wet bulb temperature, and you can use charts like this to figure out what the relative humidity is. Here's another relative humidity chart. I'm not going to worry about that because I don't think you necessarily have to worry about making these calculations. You can see some examples over here. Over here, there's a chart of different levels of humidity. We're not going to ask you on the exam to figure out because you don't have the available chart, so there's no real way you can figure that out. But the point is, relative humidity can be calculated by figuring out either what the dew point is or what the wet bulb and the dry bulb temperature are. The way you measure relative humidity is hygrometer. And that is, there's a cyclometer and a hydrometer, but the idea is you compare the wet bulb temperature to the dry bulb temperature, and again, wet bulb meaning what something, if you dip in water, what its temperature would be, and dry bulb meaning really the temperature at which it condenses is the wet bulb temperature. When I used to teach earth science, what I used to do is we'd have a little experiment, and the way we do it is we take the regular cup of water at room temperature and use that to figure out the dry bulb temperature, or you could use any kind of thermometer, any kind of external thermometer to figure out what the dry bulb temperature is. And for the wet bulb, what we would do is we would put like a cup of water or a soda can and put more more ice cubes in it and see when it condenses, what temperature the outside of the soda can condenses, and that's the wet bulb temperature. And then you compare that, and then you use a chart to figure out the relative humidity. And finally, we have the concept of adiabatic heating and cooling. And that occurs when temperature can change even when heat is not actually added or taken away. Obviously, the easiest way to make a change in temperature is to heat it, and the easiest way is to make it cooler is to cool it off. But you can also increase or decrease temperature by changing the pressure, by compressing the air, in other words, compacting it, increase the pressure as the air goes closer together, or by letting it expand. If air is compressed, in other words, there's high pressure from all sides, well then the molecules are going to be closer to each other, they're going to bang into each other more, it's going to cause more motion, and therefore the air will warm. And that's why when you have air from a mountaintop that comes down towards the ground, it's going to increase in pressure. Remember, we saw before how in the troposphere, the lower you are, the higher the air pressure. As air mass comes down from a mountain, it's going to go into higher and higher pressure. And as it goes into higher and higher air pressure, it's going to increase in temperature because the molecules get squeezed closer and closer together. So descending air is compressed due to increasing air pressure. The air expands. In other words, the air, if the opposite, if it goes up, it will do the opposite. If it goes up, that means it goes up a mountain, and air mass goes up a mountain, that means the air pressure is decreasing. And if it's decreasing, that means the air masses are expanding, and therefore it's cooling off. This causes a type of fog called upslope, because since the air is cooling off, the moisture is condensing. Remember, moisture in warm air can hold a lot more moisture without causing condensation, without causing fog. So as air rises on the side of a mountain, well, it gets cooler and cooler, and that causes the air to condense. That causes the air to become liquid, and clouds to form, and fog to form. So they call it upslope because it happens when it's going up the slope. So rising air will expand due to decreasing air pressure, and stability happens when the environmental lapse rate well, it's when they're equal. I don't even know what the sentence means, so I'm just going to cut the whole sentence. But basically, stability happens when you have the air is staying constant in terms of temperature, pressure, and all those other factors. So that's basically air pressure and temperature and the relationship between them, and moisture as well. Higher pressure usually means lower moisture. Also, higher pressure means higher temperature, whereas lower pressure means cooler temperatures, and it also means, generally speaking, lower pressure. Now we're going to get further into meteorology and looking at weather patterns and storms. And weather patterns all start with air masses. Now, air masses are just bodies of air that usually have characteristics of being cold or warm, or wet or dry. It's an immense body of air that's characterized by similarity of temperature and moisture. The main thing that determines whether a source of air is going to be cold or hot or wet or dry is where it forms. It takes a few days. The source region is where it started, where it acquired its properties, its moisture or its dryness, or its heat or its coolness, or both. And because it takes a few days for an air mass to move across, the region under the influence of that air mass experiences fairly constant weather. That's called an air mass weather. Let's look at this diagram over here for a moment. You can see over here what the different examples air mass regions over here. These are two different diagrams that you see they're slightly different in the summer and the winter, but they're the same basic idea. This is a map of the United States, of course, over here. I don't know if you can see it through. Here's the Rockies, here's the US, here's Canada up here, here's Alaska way over here, Mexico, South America. Anyway, the warm air fronts tend to form south near the equator, whereas the cold air fronts tend to form north near the poles. The wet air masses tend to form over the water, common sense, because a lot of water evaporates, whereas dry air masses form over the continents. So, for example, you could have On the top diagram over here, you can see these MP forming over here and over here. The reason why this is cool and wet, cool and humid, is because it's cool because it's formed pretty far north, and it's wet because it formed over the ocean. On these red ones or these orange ones over here, whatever color that is, are southern, and they are also moist. They're MTs. They're maritime tropicals. MP is maritime polar, wet and cold. MT is maritime tropical, which is warm and humid. They're warm because they formed from pretty far south, and they're humid because they formed over the ocean. Then you have the continental ones, the Cs. C stands for continental, where it forms in a warm area but over land. So you have CP, which stands for continental polar. The continental polar air mass, the reason why it's continental is because it forms over the land, over the continent, and that's also why it's dry. And polar because it's cold. It forms up near the poles rather than near the equator. In the winter, you can have very cold and very dry, the CA, the continental Arctic air mass. Arctic, very, very cold, and it forms from way north, and it also causes very dry weather because it forms over the continent. In the summer, you can see it's pretty much the same, but slightly different ones. The tropical ones are bigger, the polar fronts are a little bit smaller, and you can see this also have this little one, this CT, continental tropical, hot and dry air mass over here in the summer pattern. Because the reason why it's called continental tropical is because it is continental, it's dry because it forms over land, and it's tropical because it forms from the south. Essentially, things that form in the south are going to be tropical, they're going to be warm. Things that form in the north are going to be polar or Arctic, which means cold. And maritime means they form over the water. Polar, they form over, also a maritime, they form over the water, and continental, they form over the land. So you can have dry and cold, that's continental polar or continental Arctic. You can have dry and warm, that's continental tropical. You can have cold and moist, which is maritime polar, and you could have warm and moist, that's maritime tropical. Okay. These are just the list over here. We saw this already. Continental polar is cold and dry, like from Canada over here. You have continental tropical, which maritime polar, which is cold and humid. Sometimes like the nor'easters that we get. The reason why they're called nor'easters, these snowstorms that we get sometimes, is because they come from the northeast. This is New York right over here, and we get the maritime polar air masses, the ones that very often bring big snowstorms. Where do they come from? Well, they got to come from the east because they're cold, and because in order to be maritime polar, carry a lot of moisture, they have to be maritime, so they come from the northeast. That's why we call them nor'easters. Okay, you also have maritime tropical, which comes from the ocean, but it also is hot. Comes from the Gulf of Mexico, comes from the southeastern United States, this area, or this area, or this area. And again, this is really just a reiteration. If it's polar, if it's high latitude or cold, and tropical if it's low latitude and therefore warm, continental if it forms over land and is dry, and maritime is when it forms over water and therefore is humid. In the United States, you have continental polar and maritime tropical air masses. Those are the ones that are the most important. Really, it's going to be cold when you have air masses like this, which are continental polar, continental cold, and it's going to be warm when you have maritime tropical air masses. Over here, like a weather forecaster in Kansas, Missouri, or Ohio would probably focus on one or the other. That's right over here, Missouri, Ohio, whatever, which is right around this area of the country. So what they're looking at, are we going to get empty air masses from down here, which probably means it's going to be moist and warm? Or are we going to get continental air masses from down here that are cold and from up here that are cold and dry? So forecasters over here would definitely look at which way are we going to get. The bigger the air mass, of course, the longer it will last. Now, the difference between an air mass, this should really be a warm air mass. I'm going to change this to air mass because we didn't get to fronts yet. A warm air mass, it takes longer to come. And then the longer it takes to come, when air masses collide, when you have a warm air mass and a cold air mass coming together, well, then you have a front, but you also have a high probability of rain because the cold air forces the warm air up because the cold air is heavier than warm air. So they kind of come together. well, I think we have it down here. Yeah, if you have a cold front and a warm front that come together, cold air mass and a warm air mass to come together, well then the warm air gets pushed up because the cold air is more dense, and as the clouds rise, they condense and rain tends to fall. Okay, and again, this is what we discussed before. In this, you have a lot of maritime tropical air masses that come from down here in continental polar. So weather forecasters that are around here are going to look at, which one is coming. This one's coming, it's going to be cold and dry. This one's coming, generally speaking, it is going to be warmer and wetter. Next, we are going to look at fronts. Fronts are really just the borders between air masses. You have a cold air mass and a warm air mass, a continental air mass and a tropical air mass, and they're next to each other, and the leading edge of an air mass is called a front. A front is a boundary that separates air masses of different densities. Obviously, colder air masses tend to be more dense than warmer air masses, so one air mass is usually warmer or more moist than the other. Warmer, less dense air overlies, which means rises above, the denser air because heat rises. That's really what causes rain to happen with fronts, because when a front comes through, the cooler air pushes the warmer air up, and then the warmer air's moisture condenses, and then it rains. The types of fronts, you have warm fronts, which is pretty obvious. A warm front is where you have a warm air mass moving in. A cold front is where you have a cold front moving in. The warm air when a warm front moves in, the air condenses and brings down moisture on the cold air mass. Cold front moves in more quickly. Then you have a stationary front where you have a border between the air mass, but they're not moving. They're just kind of staying still. They're not moving into each other at all, and so they're moving parallel to each other. So it's not really going to cause a lot of unsettled weather. And then you have an occluded front. An occluded front is when a cold front, which is moving fast, kind of sneaks up behind a warm front and takes over it, and it causes very complex weather because you got the mixture of the cold air and the warm air and the rising warm air, etc., etc. Now, in terms of what the fronts look like, you can probably imagine what they look like, but here are some diagrams. A warm front is when you have a warm air mass coming in from the left over here. Then they tend to rise, and you have all these different types of clouds form. A cold front is when you have a cold front moving in, and that pushes the warm air up. Well, the cold air is always going to move in under the warm air. Then you have an occluded front, where you have a warm front and a cold front, and the cold air kind of overtakes the warm air. And that very often causes heavy rain because it drives the warm air up. Over here over here you had a warm front which was moving this direction. You had a cold front that was moving in behind the warm front, and here, so the occluded front happened when the cold air overtook the warm front and forced the warm air up as the two cold air masses linked together. I'll show you what a map with these things looks like. This is an example of the eastern part of the United States with a warm front and a cold front. You see a cold front coming in here, and you have a warm front over here. A cold front is symbolized by these blue triangles, whereas a warm front is symbolized by these red semicircles. Now, in terms of the air mass, you can probably imagine this probably started off as a continental polar air mass. It's cold, so it probably came from up here and kind of swung around down here. And this, and you can pause it and take a moment to figure out what kind of an air mass do you think this is. Well, it's okay. Now that you've unpaused it, you can figure out it's probably a maritime tropical air mass. It's warm, so it's tropical, and it came from this area, which is mostly water, and so you're talking about a maritime tropical air mass over here. So, behind over here, you probably have this maritime tropical air mass that's behind this warm front. Then you have the cold front that's going to come in here, obviously, and make it a lot cooler. In fact, if you look at the temperatures, you probably can't see it because it's very small. But this is in March, so it's kind of in the springtime. Behind the cold front, you see a cool air mass. You see 59, 59, 62, 54, 58. You see these in the 50s, most of these temperatures over here. Whereas over here, look at these temperatures: 82, 81, 77, 82, 82, 81, 74, 74. Over here you have temperatures in the 70s and 80s because this is behind the maritime tropical air mass, so this is still warm, whereas this is cool. Now, I would imagine if this is 4 p.m. by that night, by later on, this front, or the next couple of days certainly, this cold front is probably going to wipe through here, and instead of seeing 70s and 80s over here, you're probably going to see 50s and 60s over here like you did in this area. So this is really the movement of an air mass from here all the way down through here. That's why it's a front. This I happened to pick up also, which was, I thought, a very interesting map of the United States. The headline of this article is "This weather map. The weather map today is completely insane." Look at this weather map. This is actually from December 6th of this year, 2013. You can see in the middle of the country, in the upper Midwest, you have, or in the mountain states, you have very, very cold temperatures. In Montana, you have temperatures of negative 25 degrees, negative 15, negative 10, zeros all the way through the middle of the country. Even down through Texas, you have very cold weather in the 30s. In Phoenix, where it's usually very hot, you have 38 degrees. Generally, in California, you had very cold. You had basically really cold weather throughout the country, except down here in the southeast. In the southeast, you had nice warm temperatures, 60s and 70s in Georgia and the Carolinas. And the reason for that is, and if you were asked why is that, why would this happen, well, the answer is pretty apparent. They have maybe a continental polar or even a continental Arctic air mass that's pushing down through the middle of the country from Canada, that started all the way up here and is causing this tremendously cold air mass over here, whereas down here it hasn't quite hit yet. You can see this little line over here. You're laughing today, North Carolina, but just wait until the weekend. And the reason for that is this is North Carolina, which is nice and warm at this point, but you can probably figure what's going to happen as this air mass comes down. This area, although you don't see the signs over here, this area is obviously a cold front that's expanding this cold weather in a southeastern direction. So the passage of a front through the area within a span of a day could very often change the weather, of course, and change the precipitation. So just for example, and this is a pretty obvious one, if on a given day in New York City the morning starts off with snow, then it turns into rain, and then it becomes sleet, and then it becomes the ice, the water on the ground that fell during the day becomes ice. It's a pretty typical weather pattern that you see a lot. What probably happened is that a cold front first passed over the city, then maybe you had a warm front and a cold front, and then basically the warm air was stuck between two patches of cold air, which turned into snow in the morning and ice late in the afternoon. And here's another example of a map of the United States with all different types of front. This is also a real map. This happens to be from October 21st, 2013. So you can let's take a look at some of the things that are apparent in this area. You have a cold front, which is coming down through here, probably again a continental polar air mass, probably coming down from the middle of Canada over here. In fact, as it so happens, I remember this day, there were heavy snowstorms over here in the Dakotas and this area in the upper Midwest of the country over here, because of the cold front. Even though this was October, it's kind of early for snow, but because of the cold front, it was cold enough for it to snow. There was a warm front over here, on the other hand, in the Great Lakes region, so areas like Ohio were probably significantly warmer than average. Now you can't really see the temperatures; they're too small, but I don't even know if they're on this map. But whatever the temperatures are, I can assure you that right over here it was a lot colder than right over here because the cold front hadn't yet reached it there. The cold front being the arrows, and the warm front being the semicircles, the red semicircles. You see a cold front out over here, and over here you have an occluded front. The occluded front is symbolized where you have both the arrows in one direction, and the semicircles in the other direction. So you can see, for example, in Florida, central Florida, the Orlando area over here, you have an occluded front, which of course means it's much more likely to be rain and very violent weather. You also have the H's means high pressure and the L's mean low pressure. So for example, over here where you have the L and the cold front moving through, That's why you had snowstorms over here, because you had low pressure moving in. You can see the pressure numbers. 1002 is relatively low, whereas 1022 is relatively high. Like the H's are 1025, 1022. The L's are 1000, 1003, 1002. So here you had low pressure and cold front. That's why on this day you had a snowstorm, because you had a cold front coming in, dropping the temperatures, and you had low pressure coming in, which leads to moisture and wet weather. High pressure areas had relatively nice days, like over here. They probably had, it was on the other side of the front, so over here in Colorado they probably had or in Utah they probably had nice weather because they had high pressure and they were on the other side of the cold front. They probably had a warm air mass. And so this is just an example. You can go to weather.com and find maps like this every day to determine what's happening in the various areas of the country, but this is just one example of a situation in which you would have different fronts in different parts of the country, and there'd probably be snow or wet precipitation over here because of the combination of cold and low pressure, occluded front, like probably violent rain over here, warm front over here, nice weather up here, etc. Next, we're going to take a look at some other phenomena regarding weather. Clouds is one example. Clouds, of course, are just water vapor that is condensed and up in the atmosphere. They can be high clouds, they can be low clouds, and they are called different things based on where they are. High-level clouds are generally called cirrus clouds, or cirrostratus, cirrocumulus. Either way, anything when you see the CIRR at the beginning of it, that means high clouds, and relatively, they're actually composed of ice crystals because they're so high, the weather's so cold up there where they are, but they're high, the puffy clouds that don't usually cause much rain. Then you have the mid-level clouds, which are around the middle of the troposphere. They can be made from liquid water droplets or ice crystals, or a combination. Those are the altostratus or the altocumulus. Look for alto. Again, those don't cause the rain. The real rain clouds are the foggy clouds or the low clouds. The low-level clouds are the lowest level of the atmosphere. Those are liquid droplets, or if it's in the winter, it could be snow droplets. But these are called stratus clouds, cumulus clouds, stratocumulus, nimbostratus, whatever. The point is that all these clouds are low level, and these are the ones that are the dark gray clouds, the ones that cause fog, and the ones that cause precipitation. But cirrus clouds are way above are high. The altostratus and altocumulus are in the mid-level. Then the rest of these are the low-level clouds. So the lower ones, the cumulus clouds, the different types of cumulus clouds, these are the ones that are the gray ones. These are the ones that produce serious storms. And different level clouds means different things in terms of upcoming weather. Cirrus clouds, followed by cirrostratus clouds, even though they're high clouds, tends to mean that a warm front is approaching. And the low-level clouds produce rainstorms. Cumulonimbus clouds, nimbostratus clouds, both of those, if you recall, those are the lower level clouds. Those are things that tend to cause the rainstorms. If you want a little diagram, you can see the cirrus clouds are way up here. Very high. You have the mid-level clouds over here, the altocumulus and altostratus clouds. Then you have the real storm clouds over here. The gray low clouds are the nimbostratus clouds. The cumulonimbus clouds are the very, very thick clouds that cause rain and thunderstorms and all that. And the other clouds, the stratus clouds, are lower, but they're not necessarily storm clouds. Now, all high or low pressure systems, if you have a high pressure air mass or a low pressure air mass, it's going to cause the wind to swirl around in that area, because high pressure causes the wind to blow away from the high pressure, and low pressure causes the wind to blow towards the high pressure. All wind is a difference in pressure. You have high pressure on the left and low pressure on the right, the wind is going to blow from left to right. And when you have a high pressure air mass in the middle, that is called an anticyclone, and when you have a low pressure in the middle, it's going to cause a cyclone. The reason for that is that when you have low pressure in the middle, all the wind is going to blow in towards it. Now, in the northern hemisphere, when winds blow and they in a circular pattern, they tend to go toward the right. So as they blow in, they're going to blow towards, like for example, if you have a cyclone, the low pressure air is in the middle, and all the air or all the wind tends to blow in towards it and swirl around it. So let's say, for example, again, let's say you have a low pressure system in the middle, and well, we'll use blue for high pressure, and you have high pressure over here, and you have high pressure over here, and you have high pressure over here, and you have high pressure over here. So what's going to happen is, we'll use green to indicate the winds. The winds will all tend to blow from the high pressure towards the low pressure. But as they move in a circular pattern in the northern hemisphere, because we have because of something called the Coriolis effect, we're not going to go into that, but again, you can Google that if you're curious. The wind patterns tend to move to the right side, so as they're circulating. So as it moves in, it tends to go in this direction as it comes in from this direction. In other words, wherever it comes in towards the low pressure system, it circulates to the right. So eventually, what you're going to have is a system where everything is circulating in this direction to the right, which is going to be counterclockwise. Clock goes like this, so you're going to have a strong counterclockwise system with a low pressure in the middle. Major storms like hurricanes and whatnot are typically cyclones, where you have a low pressure system in the middle, like tornadoes, whatever, and so all hurricanes in the northern hemisphere, like in the United States, move in a counterclockwise direction, because they all come in towards the middle, and according to the Coriolis effect, they hook to the right, which causes it to move in this direction. I have an example of a shot of a hurricane. I believe this is a hurricane, or major storm. You can see over here this thing in the middle, the eye of the storm. It must be a low pressure system, a very low pressure system, and all the clouds are swirling in, and I'm sorry, that wasn't such a good picture. Let's try this one instead. Anyway, so let's say you have the eye of the storm in the middle over here. This is a low pressure system. And look where all the clouds are going. All the clouds are, I think the one I did previously might have been in the southern hemisphere. And so the winds may have been clockwise. But anyway, from this example, you can see clearly that the materials are all going in a counterclockwise direction. All the clouds are swirling around this way, because this is a typical cyclone. Now, in anticyclone, let's go back this. Remember, this was the way a cyclone worked. An anticyclone is the opposite. That's where you have the higher pressure in the middle. Let's say, for example, instead of a low in the middle, you've got a high pressure in the middle, and all around it, you've got lower pressure. So you've got low over here, low over here, low over here, and low over here. And the wind is going to go out from the middle into the low pressure, so the wind will go like this, and again it'll hook to the right, because everything in the northern hemisphere hooks to the right, and from here in this direction, and from here in this direction, and in essence it will be an outward moving circulation, and the circulation this time will be clockwise, because it's going from the inside to the outside, and it's all hooking, so it's going to be moving around in this direction. Now, I can't show you a picture of a major storm that is an anticyclone, because on the contrary, an anticyclone is usually going to be nice weather in the middle. Actually, I do see one example of an anticyclone on a much bigger area. Now you can see there's not much of a, before it looks like there was a major storm, and there probably was a major storm. Here, there's not really a major storm, it's just a bunch of clouds. It looks like pretty nice weather, but you got that high pressure in the middle at the epicenter over here, and but all the clouds you can see are blowing in a clockwise direction. And so the distinctions are, well, a cyclone, which is a low-pressure system associated with rising air, what happens is as the high-pressure air comes in, it pushes up the air that's in the middle, the cooler air that's in the middle, or whatever air is in the middle. It's a center of low pressure. Pressure decreases towards the center, and then after it eventually passes, of course, the pressure would then rise after all the high-pressure air gets back in. The anticyclone, on the other hand, is associated with air falling, because the air is coming in from the outside. It's a center of high pressure, and that generally causes fair weather. It generally causes nice weather, because the storm clouds get blown out. And then afterwards, after you have the high pressure fills up the middle, then after you have the high pressure moves. Let me start again. The anticyclone, the high pressure system, is the air blows out from the middle. And therefore you're going to have nice weather, but it also means that eventually it's going to kind of stabilize with the outside because the high pressure is going to blow out, causing the surrounding area pressure to increase. And so that's an anticyclone is a high pressure system which is associated with good weather, whereas a cyclone is associated with more rough weather. In the northern hemisphere, it blows counterclockwise because it blows inward. In the southern hemisphere, it also blows inward when you're talking about low pressure. But in the southern hemisphere, it would be the opposite because in the southern hemisphere, instead of blowing to the everything going to the right because of the Coriolis effect, everything goes to the left because of the Coriolis effect. So in the southern hemisphere, a cyclone would be clockwise, and an anticyclone would be counterclockwise. But everything else on these slides are really just indicated in terms of what we discussed before. And this is an example. We discussed this a little before. An anticyclonic flow is where you have high pressure in the middle, in the northern hemisphere, of course. Everything blows to the right, causing it to go clockwise direction in the northern hemisphere. In a low pressure system, everything goes towards the middle, and the air gets pushed upwards. Over here, everything gets pushed out of the ground, and therefore the air that's above falls to take the place of whatever was blown out of the high pressure system, whereas in the low pressure system the air blows in, pushing up whatever was already sitting there in the middle. It's another reason why anticyclonic weather turns weather nice. High pressure turns weather nice because it blows the air out, causing the other air that was higher to fall and warm up, and therefore be less likely to rain, whereas in the low pressure system you have weather in the middle, and then when air comes in, pushes it up, and as it rises, it cools, and therefore is more likely to rain. The two major types of cyclones, the two major types of really, really bad weather that you could have are tornadoes and hurricanes. And that's because tornadoes and hurricanes are both cyclones. They're both low pressure systems where you have really low pressure in the middle, and you have a lot of winds and rain that swirl around it. Tornado, of course, is a violent windstorm, and what happens is really with a tornado, there's usually in the middle of another storm, so the air is kind of unstable and things are swirling around all over the place. And what happens is you have a really enormous low pressure, very, very low pressure system that gets caught in the middle, and all of a sudden the wind starts swirling in toward it, and you get this very, very high rotating column of air that extends downwards from a storm cloud, a cumulonimbus cloud, which is as we saw before, the most violent type of cloud. And the low pressure causes the air to rush in. The winds can be up to 300 miles an hour. They occur most frequently in spring and most common in the Midwest, where there's a lot of flat ground, where the wind isn't broken up by a lot of trees and things like that, and are very often associated with severe thunderstorms when the weather is very unstable anyway. A hurricane is kind of similar to that, but a hurricane is really when it is a much bigger scale. The hurricanes are the most violent storms on Earth. They may not have the same kind of winds as tornadoes, but of course tornadoes are relatively small, all within a square mile or so. Hurricanes can be hundreds or even thousands of miles in terms of their effect. The wind speed of hurricanes is in excess of 174 miles an hour. That's what starts a hurricane. I think that's a Category 1 hurricane, all the way up to Category 5, which is something like 200 miles per hour. It's a cyclonic circulation. In other words, it's a low pressure in the center. That one that we saw before, that really big storm, that was probably a hurricane. In fact, I'll find you an image of a hurricane. They're relatively easy to find over here. You can see this is an image of Hurricane Katrina, which caused all of the damage in New Orleans and those areas. This is Louisiana. This is, I guess, when Hurricane Katrina was first starting to make landfall. You can see how big it is. And it's a low pressure system in the middle. You can see this is the eye, the low pressure in the middle, and all the swirling clouds are, of course, going counterclockwise, like any cyclone. Things are going around in this direction because things are going to the right while moving into the circle, into the middle, kind of like this, all the way into the middle. And this is an example of a hurricane, and there are lots of different images of hurricanes. You can see many of them look pretty similar. They all look basically the same. This was Hurricane Irene that happened a couple of years ago. Hurricane Sandy, which you may recall just happened less than a year and a half ago, was one of the biggest hurricanes of all time. I mean, you can see how enormous it is, even compared to Irene, which we saw before, which was maybe Katrina, I'm sorry, even Katrina, which was something like this big, you can see how absolutely enormous Hurricane Sandy was in terms of compared to even other hurricanes. It was really tremendously huge, one of the biggest hurricanes of all time. So in a hurricane, it gets its energy, just like tornadoes do, and just like cyclones in general, from the differences in pressure between the center parts of the storm and the outer parts of the storm. And it usually forms between 5 degrees and 20 degrees, which means it forms in the tropics. It forms where there's warm air. The warm air tends to be less stable, and it tends to cause, rising air, which forms, basically you have rising air in the middle, and because it's very warm, and that shoots up, and that causes the pressure to drop dramatically, and more pressure, more wind to move in, which causes hurricanes, and that's why they usually form in the tropics. And so by the time they come north, they may be weaker. And that's why usually when you get up as far as New York, the hurricanes are a little bit weaker. But of course, with Sandy, it didn't work out like that. But usually it does work out like that. Usually the major areas that are susceptible to hurricanes are areas near the tropics, areas like Florida, Louisiana, Puerto Rico, things like that. A hurricane forms in tropical waters. It doesn't form in the South Atlantic or in the eastern South Pacific, but usually in the Caribbean Sea, in the Middle Atlantic area, near the tropics. That's where tropical storms and hurricanes usually form, and they come from condensing water vapor. Water vapor rises very quickly because of the heat, and that causes kind of like a vacuum in the middle, a very, very low pressure system. So it really needs warm water. Without the warm water, you wouldn't have, if it's on land, well, you wouldn't have the moisture necessary for a hurricane, and if it were on water, I'm sorry, if it's cold water, then it wouldn't cause the heat to rise quickly enough. So you need something to you need a very warm, moist environment in order for a hurricane to form. Initially, it starts off with a tropical. Very often, it starts off as a tropical depression or a tropical storm. Up to 38 miles an hour, it could be called a tropical depression. Up to from 38 to 74 miles an hour, it's called a tropical storm, and then over 75 miles an hour is where it's finally called a hurricane. Now, a hurricane, as long as it's over water, can keep building and keep getting stronger. That's what happened with Hurricane Sandy. Hurricane Sandy kind of came up the East Coast. I'll show you the path of Hurricane Sandy. I remember last year when this happened, we were looking at this day by day to see what would happen with Hurricane Sandy, whereas many hurricanes will come in over Florida or over the Carolinas or through the Gulf of Mexico, and once a hurricane gets over land, it's going to weaken dramatically because it's not going to be able to draw more water because it's not over the water. Hurricane Sandy, on the other hand, one reason why it was able to be so big by the time it hit New York and New Jersey, first of all, it was huge, but aside from that, it also stayed over water the whole time until it hit the upper eastern seaboard over here, so it was able to intensify and get even bigger as it moved along. So it was able to hit the East Coast when it was still very, very big. Eventually, if the water gets cool, or if the air temperature around it gets cool, or if it crosses onto land, then it is going to start to weaken. It's going to diminish as it moves over cooler ocean water or moving onto land, or in general, if it moves into an area where it's able to equalize its pressure, then it will tend to weaken, and it will then become either a tropical storm or no storm at all. You can see over here what a cross-section of what a hurricane looks like in the middle. You have the eye of the storm in the middle, and all of the rain bands are circling around the hurricane. And we saw the other diagrams, which I think illustrated maybe even better than this one. And finally, the last chapter we are going to deal with is chapter 20, and that deals with world climates and global climate change. First of all, climate in general is a little different than weather. Weather means in an individual day or an individual week, for an individual city, whereas climate means an entire weather system for a long period of time and a large geographic area. The most important elements of any climate are really the two things that are temperature, how hot or cold it is, and the precipitation, how much does it rain or snow. The world climates are the combined effects of all the temperature, precipitation, and circulation of air in terms of how it affects the world in general. And we're going to look at some climates. And there are 6 basic types of climates that are each divided into subclimates. The 6 basic types of climates, as you can see over here, are humid tropical, which means, of course, well, moist and warm. Then you have dry, and by the way, of course, moist and warm could be wet tropics or tropical wet and dry. In other words, there could be like little different systems for different, for different types of climates. This map is, of course, just the Western Hemisphere, just North and South America. You could probably do the same thing for Europe or Asia. You have dry climates, which are the steppe, or like low latitude grasslands or deserts. You have humid middle latitude, like moist, where you have dry summers and humid winters, things like that, different subcategories. We live in this middle one over here with, actually, I'm sorry, well, I shouldn't say we. In New York, we actually live more like in this one over here, the fourth category. The first one is humid middle latitude with mild weather that have relatively warm winters and relatively cool summers, and then you have humid middle latitudes with more severe winters. An example of a middle latitude with a mild winter might be something like the south of the United States. The northeast of the United States and north central would be this area, where it's humid and middle latitude, but relatively cold. Then you have the polar, which is tundra or ice cap, where it's extremely cold. And then you have the ice caps, which of course is on the poles themselves, or Greenland, etc. And also highland is the last one. Highland means the climate that you find in mountains. Okay, so those are the 6 basic types. And again, you don't have to memorize these because the words themselves tell you what they are. Tropical is obviously going to be warm. Polar is going to be cold. Middle latitude is going to be somewhere in the middle. Humid is going to be warm. Excuse me, moist with a lot of rain and precipitation. And arid is going to be dry, or it might just say dry, in which case, of course, it means just plain dry. And here are the slides that indicate that. You have humid tropical climates which have no winter, and they have a mean temperature above 18 Celsius, which is about 65 degrees, 64 degrees Fahrenheit. So really there is no winter. These are the tropics. Maybe, South Florida is certainly like that in the United States. Those are humid tropical climates, a lot of Africa. You have dry climates that are hot and dry. The evaporation exceeds precipitation. There's a constant water deficit. That's in deserts like the Sahara Desert and in Arizona in the United States. They have high pressure. And their boundary, in other words, how they're marked out, depend on precipitation, temperature, and the seasonal distribution of precipitation. If there even in some areas that are kind of a little like desert, there could be rainy seasons where they have a little bit more rain. Also, within dry climates, you could have arid or desert, which is like desert, like the Sahara Desert or the Arizona Desert, whatever it is. And you could also, even within dry climates, you could have semi-arid, which means partially dry, or steppe climates. Steppe means like grassland climates, which areas that kind of surround deserts, or maybe deserts that are not quite sandy deserts, but deserts that have a lot of vegetation, like a lot of the Arizona Desert as well. You also have, under dry climates, these deserts in general are usually located around 30 degrees latitude, and the reason is because those are high pressure belts. Generally speaking, at around 30 degrees latitude, you have areas of high pressure, and therefore they tend to be much drier than areas in the southern, near the equator, or areas further north. So because of that, a lot of the deserts, for just another example, I hate to use this example again and again, Phoenix, Arizona, that desert is somewhere around 30 degrees latitude. So these high-pressure belts cause moisture to blow away and make the area very dry, and therefore the air sinks and warms, because when you have the air blown out of the way, the warmer area, or the air from the upper part of the atmosphere, falls down, and that tends to lead to areas of very low rainfall. And the sky, generally they have clear skies, maximum sunshine, droughts sometimes as well. Examples: northern Mexico, southwestern United States, North Africa, etc. In the mid-latitudes, in other words, further like inland, you also have some dry climates because they're far from the ocean, which is the source of maritime air masses. They're also very often on the leeward side of mountains, which means the side of the mountain that's going down. In other words, if you have a mountain, and just a little quick example here. So, well, that's this. I'm sorry, the screen isn't big enough. But here's the windward side. Here's the leeward side. Here's the other side. So the air comes from this direction. The wind comes from this direction, and it goes up. And as the air rises, the air cools off, and whatever moisture you have usually condenses and falls. Therefore, if you're over here, you're generally going to have dry air because all the rain kind of fell as it was going up the windward side. So the leeward side, very often you have air that's more dry than you do on the other side. And these areas are known as rain shadow deserts because they're blocked by the mountain from the rain. Most are in the northern hemisphere. Examples would be a lot of the middle part of the United States, places in the Midwest where you have grassland. They're relatively dry, not as dry as deserts, obviously, but still drier than other areas, like where you have rainforests and things like that. If you look over here, this is a world map, which kind of illustrates the last couple of points that we have been discussing. You have the desert, the arid area. You have this. This is the tropic, which means it's 23.5 degrees north. So 30 degrees north is somewhere around here. So you can see there's a lot of desert around this area of the world, the Gobi Desert, and in the United States you have the Mojave Desert, Sonoran Desert, which is where Phoenix is. Mexico has some deserts. These are all things that are desert, and the brown area is the part around the border of the desert, which are steppes, which are semi-arids, which are partial deserts. But you can see how, generally speaking, they're around 30 degrees north and around 30 degrees south, including the big desert in the middle of Australia, the outback. And that next, in terms of climate classification, we have the humid. That takes care of the dry. Well, now let's look at the humid. Now let's look at the parts that are more wet. You have humid subtropics, which are on the eastern sides of the continents. The thing that distinguishes them is that they have hot summers and mild winters. Again, southeast part of the United States, about 25 to 40 degrees latitude. And these areas, there's nothing blocking, no mountain blocking their rain, and so they're humid, so they tend to get more rainfall than the steppes or the deserts. You also have marine west coast, which is on the western side of the continent, like California, which is 40 to 65 degrees north and south latitude, kind of in the middle, halfway between the poles and the equator. And they get ocean air that blows in, and they have mild winters and cool summers. And the largest areas in Europe, but also the northwest, for example, Seattle and places like that, Vancouver, are also areas like this where it's relatively moist. They have rain and all that, but they also have relatively mild temperatures because their temperatures and their weather in general is influenced by the air that's blowing in off the ocean, which is relatively mild and relatively wet. You also have the dry summer subtropics on the west sides of the continents, like the Mediterranean climate, where it's relatively dry and relatively warm, not quite like desert though. A lot of countries in the Middle East have Mediterranean climates. Israel's an example, of course. Parts of the non-desert Middle East would be dry summer subtropics, where you have a rainy season in the winter, you have a dry season in the summer, and in the subtropics, and it's subtropical because it's not in between the two tropics. And finally, you have the humid mid-level climates with severe winters, like New York, for example, and much of the upper Midwest in the United States, where it's relatively moist but also has cold winters. Then you have the polar climates, which are the very cold climates, northern Canada, maybe the northern part of the United States, Minnesota, places like that, where it's cold, tundra, Alaska, that sort of thing, Russia. And you have the highland climates, which are mountain climates. Mountain climates are usually cooler and wetter. That's why very often, even in the summertime, you could see snow-capped peaks because it's wetter and colder than it is around it. There's great diversity of climatic conditions. If you look at Denver, for example, if you look at them on weather.com, you look at their weather, one day it'll be snowing and 20 degrees, and the next day it'll be 60, and this is kind of routine, tremendously variable. In Denver, the weather is totally unpredictable in the winter from one day to the next. In the summer also, violent rainstorms, snowstorms. Well, they don't have snowstorms in the summer, but they have very unpredictable weather. And these are best described by variety and changeability, like I just mentioned. And finally, our very last topic is that of global warming, a big political issue today in addition to scientific issue. And we're going to discuss, we're kind of going to leave the politics out, but we are going to discuss the science of global warming. And global warming is based on the idea of something called the greenhouse effect. Now, the greenhouse effect, the way a general greenhouse works is you have a glass room, or you have a big glass area, and you could put plants in there and that grow, and even in the winter when it's 30 degrees outside, it might be 70 degrees in the greenhouse. And the reason is because the sunlight rays go in the greenhouse because the greenhouse is transparent, but when they bounce on the ground and try to come back out, they're blocked by the molecules of the greenhouse itself. Here's a little diagram over here. Well, first let me finish describing it. Now, that can also happen with carbon dioxide molecules. If carbon dioxide molecules are floating in the air, well, when the sunlight comes in and bounces off the ground, some of it usually escapes out into the atmosphere. But if some of those molecules, as they're escaping into the atmosphere, bump into carbon dioxide molecules, and the carbon dioxide molecules keep them in, that could, over the long period of time, cause the temperature of the Earth to rise slightly. Now, obviously, it's going to be a very small amount each individual time, but added to the billions and trillions and quadrillions of times where molecules or sun rays try to escape and are blocked by carbon dioxide molecules, that could tend to cause a slight increase in global warming as you move, a slight increase in global temperature. And global warming, that's the basic science of the greenhouse effect. And the question obviously is, how do these carbon dioxide molecules get in the atmosphere? Well, there's always going to be a certain percentage of the atmosphere that's necessary for carbon dioxide. I mean, plants need carbon dioxide to survive, so there have to be a certain amount. But recently, because of the industrial burning fossil fuels, burning coal, things like that, the percentage of carbon dioxide in the atmosphere has increased dramatically. So combusting fossil fuels, like driving cars, factories, things like that, has added a lot of carbon dioxide to the atmosphere, and also the plants consume carbon dioxide and give off oxygen. So the more plants there are, the less carbon dioxide there will be in the atmosphere because plants consume it. Well, humans have also destroyed a lot of forests in order to make paper and in order to build houses and things like that. So that has taken a lot of the plants that would normally consume carbon dioxide out off of the Earth. And so therefore, most scientists agree that human activity is causing the extra carbon dioxide in the atmosphere, and I guess there are some people that think that the warming of the Earth is causing the extra carbon dioxide, not the other way around. But the general scientific consensus among, let's say 95% of scientists is that human activities of cutting down forests, cutting down plants, burning fossil fuels, driving cars, heating homes, things like that, have generally been increasing carbon dioxide in the atmosphere. And it's not just carbon dioxide, by the way. It's also other things like methane, nitrous oxide, CFCs. Well, methane is also a very strong greenhouse gas. Methane is also caused by other different types of human activities like farming, things like that. But the idea is that these greenhouse gases that have been released into the atmosphere have caused global warming, and the way they've done that is the sun's rays come into the atmosphere but bounce off the Earth, but some of them can't leave because they're blocked by carbon dioxide, and that has made the Earth a little bit warmer. You can see the sun's radiation comes into the ground, and when it bounces off, and as they're trying to leave, carbon dioxide and other gases like water vapor and whatnot block some of them in, and that causes global warming. Okay, what are things that are likely to be affected by global warming? Well, number one, the sea. The temperature of the sea will change a little bit, and that will cause, actually, it won't affect humans that much directly from the sea, but it will affect animals and plankton and things that live in the sea. But more important for us is coastal areas. Homes and creatures on low-lying beaches are likely to be affected because the sea level could rise. As temperature goes up, glaciers, like in Antarctica and in Greenland, northern Canada, northern Siberia, could melt and fall into the sea, and that causes the sea level to rise. And if sea levels rise, well, then coastal cities could become flooded. That's one major problem with global warming. Another area, in places further north, like Alaska, the ice sheet can melt, shrinking the size of the land area. Also, I mean, just one other thing is that things that were built into the ice, like in northern Alaska, if the ice melts, the structures that depended on the ice for stability might also end up falling down. Human activities could also decrease global warming. Just like human activities have increased global warming, human activities could decrease it as well, such as by reducing the usage of fossil fuels like coal, which would reduce the amount of carbon dioxide in the air, creating less garbage, which would cause less, we wouldn't have to truck garbage around as much. It would generally help the environment in that way. Driving less by biking or carpooling or walking, wasting less electricity, using solar energy. So solar energy doesn't require burning of anything. So, burning of coal or burning of gas, burning of oil causes carbon dioxide to be released into the atmosphere, but using solar energy like solar panels or wind energy, other types of clean energy, don't cause these issues and don't cause an increase in global warming. And using other sources of energy like water power, hydroelectric, wind power, and other renewable sources of energy. Of course, one of the major controversies in the global warming idea is that some people will tell you that there hasn't really been global warming or that global warming is slowing down. So we really need to take a look at the warming trends. Now, obviously, weather is affected by many factors. Just because there's been global warming doesn't mean that every year is going to be warmer than the last, because there are other factors, amount of rainfall. I remember in the early 90s there was a volcanic eruption. They said that year was cool because of that, because the particles that were floating around in the atmosphere from the volcanic eruption kept out some of the sunlight. And some years are naturally going to be warmer than others. But one year warmer than another, in other words, just because a year is cooler than last year, doesn't mean that global warming has stopped. For example, 1998 was, I think, the warmest year on record so far. So some people will tell you, well, that means in the last 15 years there hasn't been any global warming. But that's not really true, because 1998, there was an El Nino. El Nino is a type of climate pattern where some warm southern Pacific air is carried north with jet streams, making winters much milder than average. And because of that, 1998 was unusually warm. Now, if you looked at 1998 in a vacuum, you'd say, well, there haven't been any years since 98 that have been much warmer than 98, and so therefore you might say that global warming has stopped. But if you look at something like this, you'll see that you can't really look at it that way, because you can see the general trend. Here from the 60s and through the 60s and 70s, the trend was generally pretty cool, but since then it's been going up, 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 up. And even though these years over here into about 2010 may have not been as hot as 1998, you can see that they've generally been hotter than the years before. If you compare it to years back in the 80s and even the 90s, the trend is for these years to be much warmer than those years. The coolest year recently, which was 2009, still would have been a very warm year 10, 15, 20 years ago, and certainly before that. So again, you can see over here the general trend from cooling temperatures in the early 1900s, rising, falling a little, and kind of steadying off in the 40s, 50s, and 60s. But since then, it's been rising pretty steadily as we move along. So that is an important way that you know that global warming is occurring. Again, whether it's human-caused. I'm sorry, let me move this a little bit over. I don't know if you saw most of that, but if you didn't, you can see it now. What I was referring to, 2009, a relatively cool year recently, would be very warm if you moved it anywhere else. But the general trend, I think you can see pretty clearly of the of the warming trend. Okay, so that's what we have for this, and that's also what we have for basically for the course. So thank you so much for listening. If you have any questions, feel free to contact us, and good luck.